The screen is now, the slides are visible to everybody, right? So my only request to everyone is that if you have any questions, just stop me along the way, and I'll try to answer any questions you might have. I have been told that today the audience is predominantly faculty members. So this talk was originally was designed for a conference which had a lot of students at graduate level and doctoral level students. So it allows me to now be able to talk at a slightly higher level. But the talk today is actually fairly objective, or well, subjective actually, in the sense that I would like to, I know that a lot of you are actually getting into machine learning and getting into artificial intelligence. And what I would like to do by way of this talk is to hopefully get you guys to start thinking about the data that you're going to use in your machine learning application, and how the various nuances of the data that you are going to use can have a direct impact on the efficacy and the success rate of your machine learning application.
Sir, sorry to interrupt, sir. While you are teaching us, sir, we are getting continuous beeps. There is some kind of music, sir.
Those beeps are from people who are joining your sessions.
Okay, sir. I thought it is from your side, sir. Okay, sir. We'll try to mute it. Okay.
Every time a new person joins in, you get that notification sound. So I can wait for 5 minutes if that'll help. Anubhav, should I wait for 5 minutes?
Yes, sir. Yes, please continue, sir. We will try on our end. We can see if we continue.
You can toggle the setting. There's a setting in your meeting room options where you can uncheck the option of play a sound when a person joins in. Okay, so
please
carry on. Guys, can I start?
Okay, sir. So you please continue, sir.
Okay. Once again, good afternoon, everyone. Okay, so I've titled my talk today, "Getting Data Ready for Machine Learning." So I am not saying that you already have data and you are trying to get it ready. I am saying that from a machine learning point of view, how do you get data ready? In the sense that how do you get ready for the data, right? So there's a big connotational difference between getting data ready as we perceive it and what I am trying to mention is how do you get ready for the data that you intend to utilize, right? So the broad strokes for the the broad strokes today are getting to introducing data and learning machines and their symbiotic relationship. We will I'll try to talk about how do you get your data, right? Sourcing your data, data pre-processing and dimension. How does that impact us, right? We'll look at some potential problems with the data right now, and then at the end, in conclusion, we'll talk about very quickly about some salient issues that I might have missed in the body of the talk, right? Now, once again, I realize that my audience today is predominantly faculty members, and a lot of what I have said or what I say might not necessarily be new to you guys, but so just bear with me. I hope that something new might jump across to you guys as well, okay? Anyway, thanks, guys. So data and learning machines, right? So learning machines, what are learning machines, right? I'm sure all of you understand that learning machines essentially yield a mathematical model, right? We are trying to figure out a relationship that allows us to map multimodal inputs to a singular or multimodal outputs, right? So we are trying to figure out this relationship between input and output variables, right? Or in the electronics and electrical engineering parlance, we're trying to figure out the system function, right? So the mathematical model is essentially what it's a model, right? So it'll have some parameters, and the idea of being able to compute those parameters is what the entire domain of machine learning is all about. How do you compute those parameters, right? How do you compute those parameters, right? So, and what do we have when we are? What do we get at the end? We have a well-trained model. In other words, you'll hear the language, right? A high-performing model, a high accuracy model, right? So the model aims to map some input to context-aware output, right? Context-aware output. This is a key term that you keep coming back to again and again, right? With minimal error, right? Obviously, perfection is very hard to achieve. It is almost impossible to achieve. So I'm going to use the term minimal error. And the learning, so when I say machine learning or learning machines, right, where does the learning come in? Learning is the process of arriving at those parameters, right? Now, it turns out that learning, and we'll explore that a little later, is that this learning always happens with time, over time, right? So it is iterative in nature. Learning invariably is iterative in nature, right? So we'll see how that has a bearing on this particular talk or in your particular approach towards machine learning, right? So the data that drives this learning, or the information source, is your data set, right? Database, right? And the data is nothing but a collection of samples, right? And samples are in turn nothing but a collection of attributes, right? So every sample, a sample in itself. So if I say the word orange, orange in itself is meaningless. If you think about it, it's just a noun. Orange, when you say the word orange, the person listening to that word, his or her brain automatically conjures up the various attributes associated with the orange, right? So if I mention the word orange, you automatically start thinking about its flavor, its color, the color of the skin, its texture, its vitamin C content, and so on and so forth, its aroma, right? So all these attributes are the features, right? So every sample is nothing but a collection of features, right? And again, we'll get into that. So this is just the introduction, right? So, and the higher the number of features, higher is the dimensionality of the sample space, right? So we talked about dimensionality, right? So dimensionality essentially is governed by the number of features per sample that you have or that you are intending to use, right? So one key point is that whenever you talk about machine learning, every single sample must have the same number of features, right? Same number of features. And we'll look at what happens if you have some missing features and so on, or some samples which are not complete. We'll talk about that as well later on in the talk, right? Okay. From a machine learning point of view, always remember, right? Data is your friend. Right? What do I mean by data is your friend? That the more you have of it, the better off you are. Right? So higher this is essentially a rule of thumb, right? That the more data you have, the better off you are, right? Why is that? Because learning inherently, as I had mentioned earlier, is iterative in nature, right? If you take the example of a newborn baby, right? How does it learn? How do you teach a child to learn? It is iterative in nature, right? It happens over time. It happens over multiple sample points. Right? You show that same child the letter A written in different styles, right? Like this is A, this is A, this is also an A, right? So these are the same. The information content is the same in these three samples, right? In these three samples, the information content is the same, but there are all these three are different samples from a feature point of view. From a feature point of view, they're different samples. So that's something we always must remain cognizant of, right? So the more the samples you have, the better off you are, which means the more data you have, you are always going to be better off and will have a higher success rate as far as the machine learning application is concerned, right? So and because learning is iterative in nature, it logically points to the notion that the more we see, the better we learn, right? And the higher volume of data also has a direct impact on the quality of the trained model that you will end up with. Now, quality is a very qualitative word, pardon my pun, right? Quality of the trained model is obviously a very subjective term, right? A quality which is good enough for me might not be good enough for you. But then again, the entire domain of machine learning is subjective, right? a model that performs to a certain performance level, it might be good enough for one particular application, might not be good enough for another application, right? So let's take a simple example, right? Let's say I am trying to develop a speech to text translation through machine learning, right? Now, the speech to text translation, when it is deployed, for example, transcribing a news article or a song, does not need to have a very, very high accuracy rate. But if the same algorithm is being used for medical notes transcription, then you can't afford that lower level of performance, right? The underlying engine might be the same. So anyway, what I'm saying is that the quality is subjective, but nevertheless, you can higher the data always gives you better or higher quality of the trained model, right? So, but higher volume of data is just one aspect of data. The other is variety. And then I'm sure when you get into the advent of big data, you start talking about the velocity of data as well, right? So because I'm focusing on data and machine learning, I'm not going to talk a lot about velocity. I might mention it in passing later on. But the variety of data is also very, very important, right? Very, very important. Now, why is variety such an important aspect, right? Because remember, you're trying to build intelligence. Now, building intelligence, well, requires you to first understand what intelligence really is. Intelligence is the ability to take an autonomous decision or verdict without explicit rules, right? So that second part of the statement is very is the important bit, right? Is the important bit. If you don't have explicit statements, if you don't have explicit situations, if then else conditions, that means that you are relying on your machine to be able to recognize the different kinds, natures, or forms of input that you might get, that your machine might receive. Okay, which means that in order for it to perform well, it should have at some point during its learning phase seen those different forms of inputs, right? To scale that back and to translate that back to a real world example, if I'm trying to teach a child the English alphabet and I keep focusing predominantly on the letters A through M or A through N, right? With a lower importance being attached to letters N through Z, then chances are that the child will have a higher bias towards the letters A through N, right? Because remember, learning is iterative. It is happening over time, and it is happening based on the information it is seeing, the frequency of those samples, and the number of times it has seen the samples, right? So variety means that yes, any questions?
Professor, can you please ask to mute this notification? It is really disturbing.
I understand. Anubhav.
Yes, sir.
Anubhav, you need to mute that notification in the settings. I think you'll need to go into your meeting room options, and I think you'll find that there is option of notifying when a new person arrives or leaves, a person joins or leaves, and you will need to uncheck that box.
Yes, sir. Actually, we are continuously trying for the same.
Anubhav, did you find that?
Actually, we are continuously trying for the same, sir.
May I help? You can go to the participant on top, and there it is enter and exit tone.
Yeah.
Yes, sir. Yes, sir. That option is actually blurred for us. We are not able to.
So blurred
Okay.
for you, that means you don't have the admin rights. Somebody who
No.
has the presenter, sir, probably you might have it in case you're
No,
the
not me.
presenter.
No, even I don't have it. Actually, it'll be the
Then
host.
somebody would have it, sir.
The host has it.
Host has it, sir.
Yeah. Let me see if I can do it at my end. Participant. Yeah, I can't change anything. Anubhav, you'll need to ask Dr. Manish to do this.
Problem remains same.
Anubhav,
ask Manish to make me the host, but then maybe I'll be able to change this.
I have actually reclaimed host role, sir, and even after that, using that entry and exit tone option also, the issue is not resolved, sir.
It's still not there? All right, guys, I think we'll have to just grin and bear it. May I carry on?
I think we have to bear with it, sir. Sorry for the inconvenience, but I think you should continue, sir.
My audience members, would you like to sign out and sign back in? Maybe that'll help. I think, Anubhav, if we shut down this meeting room and then when you restart it, maybe you'll be able to change this. I'm open to any suggestions from the audience members. If you guys have, if you think that'll be a better idea.
I think we may continue, sir. It's
All
not
right.
much of a hassle.
All right, sounds good. So here we go. Right. Okay. So I was talking about the variety of data, right? My point is that whenever, as a data scientist or as a researcher, whenever you are getting your data, make sure that at least you have a sufficient variety. Now, I'll tell you, I'll talk a little bit more about variety later on, and these are just introductory points about data and their symbiotic relationship with learning machines, right? Okay. Now, then the question becomes, well, okay, where am I going to get my data? So if you think about it very carefully, data is generated through one of the two methods, right? So either you get it through a physical process, which involves, relying on sensors and transducers, or you get it through a computational process, right? So you are running some computational process, which is not a physical process in a sense, and or you might have a derived process, and that generates some data for you, right? So two ways you get data. One is through a physical process, the other is through a computational process. Now, what that means is that getting data invariably has a cost attached to it. There is a certain cost attached to getting the data, just getting the data, whether you are generating your own data or whether you're getting it from somebody else, right? Which means, and particularly data coming out of physical processes are exceptionally high cost. There is always a significantly higher cost attached to data being generated through a physical process. Why? Because there is cost of manpower, instrumentation, sensors, communication costs, and so on and so forth, right? So a lot of researchers across the globe tend to rely on data being sourced from curated sites like Kaggle, Microsoft, Google Research, and Microsoft Research, Amazon. Now these big companies, and there are other, NCBI, UCI, a lot of these places, they have already curated a lot of data, and it is available freely for anybody across the globe to pull it and use it for their research application, right? Okay, now, before I move any further, and that's why I've highlighted with red, this is particularly pertinent for my faculty colleagues in the audience today, is that I'm sure you might have noticed a very disturbing trend, that a lot of students today tend to proverbially, as they say, place the apple cart before the horse, right? So they will get the data from some source, and then they will try to figure out what problem can I solve with it, right? So that's okay. From a learning point of view, that makes sense, right? That you just want to learn machine learning, that's okay, that makes sense. But as a researcher, that cannot be your primary approach. Figure out the problem you're trying to solve, right? So first of all, the baseline step has to be the problem you're going to solve, right? Or the problem you are interested in. Then you figure out whether I'm going to get data on my own, I'm going to generate my own data. And if I want to generate my own data, then there are a few checklists that you have to look at. Otherwise, where am I going to get my data from? Now, because you're going to get, if let's say you realize that the cost is too prohibitive for you to generate your own data, right? Your own process, set up your own physical process and get the data. Well, now I'm going to rely on some curated websites, right? Data from some curated website. Then there is a very high likelihood that the data the best possible data or data set that you can get might not exactly meet your requirements. And that's okay. That's okay, right? Because hey, that's the whole idea of research, right? That you can't I believe a very famous rock and roll group mentioned, right? That you can't get what you want. You can't always get what you want, right? So that's okay. But there is a bigger caution that I need to point out at this moment, especially when you're talking about data gotten from some other source. Please understand that data generated from some other source may have bias, inherent bias, particularly bias which might be geographic in nature or demographic in nature. Now, what do I mean by that? And consequently, that data set might not be a good fit for modeling a process to be deployed in a different geographic or demographic environment. Let me give you an example. Right? About a year ago, I was interacting with some state officials from the agricultural department, right?
मतलब ये नहीं बोल रहा अपडेटेड है ना लिस्ट तो वो अपडेटेड है ना वो बस वही पूछ
Sir, any questions? Okay, right. So we were talking about, and the agricultural department is sitting over, and they have a lot of agricultural data that they have been collecting over the last couple of years or 5 years, something like that, through a wide array of sensor networks, right? And I was talking to somebody, and they said that, well, we were actually trying to figure out how we can get the data for some research. And one of these gentlemen said that, you know what, our data is not currently processed at all. It's just raw data sitting in a warehouse on a server somewhere. Why don't you get data from the US or from Europe, right? Now, here's the problem. If you think about it, the agricultural data, let's look at the North American continent, right? If I were to get agricultural data or samples, data representing agricultural samples, so it might contain soil salinity, the nature of the crops, the weather patterns, and so on and so forth, right? Now, if I use that data to create a model that will predict my crop yield in, let's say, Uttar Pradesh, or North India or South India, I can guarantee you that that model will not fit. It will not perform the way we intended to. Even if I use the same kind of attributes that I might have gotten over here from the data. Why? Because data sets from a different geographical region will have its own bias, a bias that cannot be eliminated. That is as nature intended it to be, right? As nature intended it to be. So what do? There's not a lot you can do about it, except that you remain cognizant about this fact that, yes, I'll give you another example. There was a database that studied the incidence of liver failure rates in Caucasians versus African Americans. Okay. Now, I'm sure a lot of you might have traveled internationally, and you must have seen Caucasian people like the Irish, Catholic, Irish Americans, and then you have African Americans, right? You will find that they have, and if you compare those two races with the humans from the Indian subcontinent, there is a high likelihood you might have realized that they have obviously they have a slightly different genetic makeup in the sense that they have a higher tolerance for alcohol, right? We as a subcontinent, we don't need alcohol to remain warm. They have been relying on alcohol to remain warm. For example, if you go to Ireland, a lot of people drink simply because they want to stay warm. So if you that data set, it has a strong genetic bias because of the population, the population which was used to get that data. Now, if you use that database to figure out a learning machine that can model based on some biochemical test that you do over here, when the subject is prone to liver failure, chances are that your model is not going to work very well. So your database might have geographic and demographic bias as well, right? So please exercise caution when you're sourcing your data, right? Now, of course, if you're Mr. Moneybags and you have the luxury of setting up your own physical process and setting up your sensor network to generate your own data set, then a different bag of it's a different animal altogether, and you have to worry about a few other things, like at what rate are you going to generate data? So your data velocity, at what rate are you getting your data? How quickly, what is your data capture rate, right? That's point number one that you need to look at, right? You should also remain cognizant about how do you account for sensor failures, right? In case your sensor network, a couple of sensors fail, right? If they're measuring a particular attribute, let's say 2 temperature nodes sensors fail. So now so for that period of time, the samples coming in might have 0 values for temperature. Well, how do you account for that, right? Is there a noise source? For example, if you're capturing electrical data, right? Yes, Aarti, I think you've raised a hand. Aarti ji, I think you've raised a hand, please.
No, sir, it is by mistake.
Okay. Right? Okay. So if you capture electrical data, right? If you capture electrical data, chances are that you might, and particularly in an industrial context, right? So if you're capturing electrical data, and particularly in large industrial complex, you might capture your data samples might be corrupted with power line frequency interference. So you might have a hum. If you're capturing acoustic data, you might have a hum. If you're capturing impedance data, you might have some interference, right? So that kind of stuff. So my point is that as a researcher, machine learning and creating a good machine learning solution is not a simple task of patchwork, right? That you get the data, you select a algorithm, and you say, put them together. I've got this 80%, 90% training rate accuracy. I'm good to go. No, that's not machine learning. That's something that a class 10th student can do. Right? So as a researcher, it is your responsibility to be intimate with the process, the physical process that you're trying to model, right? Physical process that you're trying to model, the learning process that you're trying to model. You should understand it thoroughly. That where is my data coming from? What are the possible sources from which I can get interference in my data stream? Whether my data is coming in too fast, whether it is coming in too slow, right? Is there any noise? Do I need to compensate for the noise? If I'm going to compensate for noise, am I going to do it at the sensor level itself, or am I going to offload it to my software end, right? That kind of stuff. The other thing is, and this becomes more pertinent with high velocity data is, and given the notion that we are talking about now, getting into big data quite rapidly, is how do you store data, right? Now, are you going to store processed data, or are you going to store raw data, right? If you're going to process the data and then store it, are you going to process it in the buffer and then push it to the storage media, or are you going to push raw data into the storage media and then process it in batches offline? Now, both these things will have an impact if you are performing some real-time deployment. If the data is going to be used for a real-time application, both these approaches will have a direct impact on your performance. Right? So keep that in mind. Okay. Right. So, and it's a good thing we're talking about data pre-processing and dimensionality, right? Now, I remember in the introductory session, some of my senior professors had mentioned that, you should not pre-process data. But I mean, to a certain extent, I agree. But you got to understand that I'm not talking about, really cleaned, labeled, and, identified and filtered data. I'm saying that if your data stream has noise, which is almost impossible to eliminate. If you're capturing data in the real world scenario, you're almost guaranteed to get noisy samples. Almost guaranteed to get noisy samples. Why? Because think about it, from an electromagnetic point of view, you live in a very noisy environment. Each and every one of us is right now surrounded by at least 3 or 4 wireless signals. You might have a microwave running. You might have acoustic noise, you might have power line interference, right? So you're living in a very noisy environment, even at night when you can't hear anything, right? Electromagnetically, you are living in a very noisy environment, which means that the data that you're getting, if you're getting it from a real-time source or process, is almost guaranteed to get corrupted at some point or the other. You might have shielded sensors, you might have radiation hardened sensors, right? That's the terminology that people use when they talk about sensors which have been hardened against radiation and interference, electromagnetic interference, right? But remember, everything fails over time, which means you will at some point or the other end up with data that is corrupted. And noise, there's only one good use of noise, and I'll tell you a little later. I'll shed some light on that a little later. But for all intents and purposes, you need to get rid of it. You need to clean up your data before you can put it into your learning machine. You can give it to your learning machine to learn. Another classic analogy for that is that if you pick up apple from a tree and you want to give it to your child, you're not going to give it to your child as is, right? Chances are you will wash it first, right? You will wash it. Even if you get an apple from the market, you're not going to give it, you won't eat it directly, right? You will wash it because you are not sure whether that apple has any insecticide on it or pesticide on it, and you want to wash it, right? So there is noise. Noise is a part of life, right? So noise is one aspect, right? The other aspect is the number of features. Number of features. Now, the general idea is that higher the number of features, the more information is conveyed or available to you inherently. But then it is not a catch-all statement, right? Higher the number of features increases the dimensionality, and that comes with its own set of problems, right? One of the biggest problems is simply because is what we call as the curse of dimensionality, right? Because with every increase in the feature, every increase in the dimension, your search space increases exponentially, right? By power of x, right? Power of d. So now here's the problem. Not all features are treated alike. Anubhav, can you still see me?
Yes, sir, yes.
Should I switch off my camera? Maybe that is creating some bandwidth issues.
No, sir, actually, trying to options to mute the sound, so by mistake, I think that happened.
So this is fine, right? No
Yes.
video, it's okay, right? Okay, right. So think about it. Not all features are created equal. Some features tend to convey more information. They encode a lot more information, and some obviously don't. Now, your job as a researcher is to identify the most pertinent features. Why? Because remember, you're trying to find the perfect trade-off between the dimensionality and the computational overhead that higher dimensionality brings with it. Right? But that's just a part of the story. A higher dimensionality will lead to higher computational requirements, yes. Higher storage requirements, yes. The other more insidious problem is that every now and then, higher number of features will create crosstalk. That itself will create a noisy environment. If you have too many features, then chances are that you might end up in a...
Excuse me, sir. Your voice is not audible.
Oh, you can't hear me?
Yeah, your voice is very low. It is not audible. It is not audible.
Oh, wait a minute.
Yeah, so many people are texting.
Oh, really? I'm sorry, I had no idea. No, nobody has mentioned that my...
No, sir, actually, your voice is very
No,
much
it's
clear, sir.
very clear, sir.
Yes, sir, your voice is very clear, sir. I think that is some specific problem to some specific.
It's clear, sir. It's clear.
Okay. Should I continue, please? Or I mean, I don't see anything different. I have not changed any setting at my end, so I'm hoping that my voice is carrying clearly.
So your voice is clear, sir. Please continue.
Very clear, sir. Yeah.
All right. So where was I? Right. if you have too many features, there's a non-negligible chance that you might end up with a noisy environment, or a loud environment. In other words, irrelevant features or low information carrying features might mask the genuine information carried by significant features. So there's a good reason why we end up performing dimensionality reduction. Now, I understand that most of you, I mean, I'm sure that every single one of you must have heard of dimensionality reduction, right? And almost all of you might be of the belief that we do dimensionality reduction predominantly to lower our computational cost and storage cost, right? And that's fine. But one of the insidious things about high dimensionality is that it can create a noisy information. It can create crosstalk, right? So one of the reasons why we perform dimensionality reduction by means of PCA, etc., is that it allows you to identify which features you want to keep, which features are relevant. Now, you may ask, wait a minute, how does that help me? I know PCA, all it does is it reorders the features in the increasing order or decreasing order of variance explanation. So how does that help me? Well, it helps you because it is your job as a researcher to select or to decide what fraction of the population do you want the features to explain, or the variance in the features to explain. For example, let's say I have 10 features, right? And I sort them out, and I perform PCA, and I list out the features. It gives me an ordered list of features. When I say features, I mean mapped features. And it tells me that the top 6 features explain 90% of the sample space. The top 7 explain 96% of the sample space. Now remember, with simply increasing one feature, I'm going from a sample space that is exponent 6 to exponent 7. Now it is my job as a researcher to figure out whether the additional 1% population space that I can account for by using 7 sample features is worth the price, is worth the cost, worth the effort. So that is your job as a researcher. That's where the research scientist comes in. You have the tools. You have to identify. And conversely, I could say that reducing, going one feature less, and I can explain 93% of sample space. Hey, on any day, any given day, I would take the 93% explanation of samples, population space, if I can get away with by using only 5 features. Why not? Now, again, the statement I just made is a reckless statement. Why? But what I did not mention was that that is true if I have sufficiently large number of samples, right? If I have 10,000 samples and my 5 features can explain 9,500, can account for 9,500 samples, I'm okay with that. But if I have 10 samples, if I have 20 samples, if I have 100 samples, no, I'm not very comfortable with losing out on 7 samples out of that. You understand what I'm saying? I hope you guys understand what I'm trying to drive here. Right? It's a slightly nuanced idea. Right? And again, everything that I'm saying is being driven by my personal experience in this domain. Right? Okay. So we're talking about data pre-processing dimensionality, right? And the other thing, the other thing I want to just very quickly mention is that almost every one of you must have figured out and must have seen that your data set might contain outliers. Outliers, right? Now, most people will say that don't worry about outliers. But I'm going to say the same thing, that you don't need to worry about outliers, because from a machine learning point of view, from a classification point of view, outliers are a trivial classification, issue. Why? Let me show that to you. Let's take a single feature, right? Let's say X. Let's say let's take student scores, right? So there are student scores. And if I were to plot the entire student population and their scores, let's say I get something like this. I get something like this. Right? Now, this is what I mean. And there's one standard deviation here, one standard deviation here, and one other standard deviation here, right? So this range, this band explains mu plus minus 3 sigma, right? Okay. Now let's very quickly look at the tail end, the outliers that we call, right? So these are my outliers, if you will. I'm going to assume that any sample beyond mu plus minus 3 sigma is my outlier. Okay? Now think about it. Do I really need to worry about these outliers? If I'm trying to decide whether the student gets to pass or fail, clearly these guys are super smart. They will definitely pass. And these guys clearly are not up to the mark, and they need to be held back. From a learning machine point of view, the outliers, from a learning point of view, these outliers do not necessarily pose a significant problem, right? So you can easily eliminate outliers from your data set, and that will not only help in your learning algorithm, it will also help the quality of the trained model, right? Now the question becomes of how do I identify outliers? How do you identify outliers? If you have 100 sample points, and if you have, let's say, 3 features, no more than 3 features, then you can simply plot them, visualize them, and identify anybody who's way out there. Because outliers are what? Outliers are samples which have some or all features which have very, very extreme values. Right? Those are my outliers. But if you can't visualize your data, then how do you identify outliers? Well, 2 ways, if you think about it. If your data can be assumed to have a sort of a normal distribution or a Gaussian distribution, right? If the various features can be assumed to be normally distributed, well, you can simply reject all samples whose features lie outside that plus minus 3 sigma window, the band, right? Plus minus from mean. The other way is using thresholding, right? You can set up a thresholding factor and reject samples that are beyond that threshold value. The question becomes, how do you identify the threshold? Again, that is something which is heuristic in nature. Oh, by the way, there's one thing I forgot to mention, and this is a very seminal statement I want to make for everybody, right? I'm sure you must have realized this by now in all your exploration into machine learning, is that machine learning, most of it is heuristic in nature. It's all trial and error. How to get the correct number of features, how to figure out the right number of hidden nodes, how many hidden layers, how many clusters, what will be my learning rate, all of these things. I'm sure you must have figured it out by now, that a lot of this is heuristic in nature. There are no hard and fast rules. There are no quantitative and analytical formulae that tells you that, okay, given this data, you need to have these many hidden, right? So just like that, in the same way, when you talk about thresholding, remember that the threshold needs to be decided by you as a data scientist, as a researcher. And it should be, again, a unique trade-off between the number of samples it rejects and the volume of data that is left for you, right? So that's something, again, there's no hard and fast rule. Thresholding is dependent on your particular application, right? data scaling and data normalization, right? So again, if you were talking about data set received from curated websites or databases, chances are that you already have a very cleaned, pre-processed, scaled, normalized data set. But do you have your own data set? If you're getting raw data from somewhere, it is always, always, always a good idea to perform either scaling or normalization, right? Most applications, most machine learning algorithms expect you to give them, well, nowadays, most modern algorithms expect you to give them raw data and they'll perform the scaling for you or normalization as you wish. But if you give them, but it is always a good idea to perform data scaling. Now, why is that? Why do we harp about data scaling or data normalization? For a very simple reason that, remember, learning is an iterative process, right? And if you get into the maths behind the learning machines, you'll realize that the parameters of the model that we talk about, when we talk about the parameters of the model, for example, let's take a case of an artificial neural network. Right? I'm just doing the input and hidden weight. And now, if you think about it, there's a weight attached to each of these links, right? Each of these links. And it is these weights that are adapted when you're performing training. It is these weights that you're trying to compute through your back propagation and gradient descent, right? It's these weights. Now, if your data, and these weights are adapted based on the error which is numerical in nature, right? So you're talking about a numerical value of error. If your features are unevenly ranged, that means if your features have different ranges, then the magnitude of a higher value, a feature which has a higher magnitude will unevenly impact the learning process, right? Which means that your model will rely unjustifiably more towards that particular feature than the other features. So scaling, the long and short of it is that the scaling is always a good idea simply because it allows all features to be on an even plane. It allows the algorithm to treat any learning algorithm to treat all features equally on an even keel. It is a different matter that it also allows for much, much better numerical stability of your learning algorithms. That's just a latent advantage of scaling. All right. I hope that almost everybody has. I hope you guys understand the spirit in which I'm trying to mention this. Right? So, scaling always helps. So, scaling or normalization. Scaling simply takes your data set and maps it into the 0 and 1 range. Right. So that's normalization. And then you have standardization. You can perform standardization in which you get a new data set which will have a 0 mean and a unit standard deviation. Sometimes the shape of the distribution might be altered just ever so slightly, right? Right. The next aspect of the data that as a researcher you need to be acutely aware is data labeling or label encoding. I'm sure I assume that almost all of you have already heard about this, but let me just mention this nonetheless. And this is particularly pertinent when you're talking about supervised learning, right? In supervised learning, remember that you are presenting your sample and you're telling the learning machine what it is, right? So those target vectors, the target values, those are your labels, right? Now, first and foremost, obviously your labels need to be a numerical value, right? So it doesn't matter whether you do it as your target values need to be numerical in nature. Otherwise, you can't compute the error, right? So your target values is some numerical value. Now, here's the question. How do you decide decide appropriately what those target values need to be, right? In other words, how are you going to decide on the encoding schema of your sample space or your samples, right? Now, for example, to answer this question, yes, is there a question, somebody? Question. Anyone? Right. Okay. So to answer this question, you have to ask yourself, well, what is the output? What is the maximum output my learning machine or my algorithm can deliver? The answer to that question lies in the kind of non-linearity you're using at the output layer. Right? Now, if you remember, and again, we're talking about supervised learning, so let's again go back to the classics, right? So, if you recall, we have a non-linearity sitting at these nodes, some f dot, right? And this non-linearity is essentially a squashing function which allows you to model, and it is this non-linearity that allows you to model non-linear processes, right? If these non-linearity, if these functions were linear functions, you would have a linear discriminating machine, right? And the purpose of learning machine would be defeated, right? Because most real-world processes are incredibly complex and incredibly non-linear, right? So we have this non-linear function. Well, and these functions are designed to be saturating squashing functions, right? So, for example, you could have the sigmoid function, or you could have this tan H function, right? They're both forms of sigmoid function. Now, if you notice carefully, if you have a sigmoid function sitting in your output node, the maximum output, irrespective of what the input is to that function, maximum output can be either 1 or 0. Yeah, which means that if you're and similarly in the case of tan H, the maximum output can be 1 and the lowest output can be -1. Which means in case your samples have been target encoded with any range outside this, outside -1, 1 or 0, 1, depending on the nonlinearity, your error will never go down to 0, ever. And remember, you can the notion of training, the idea of training says that you stop training either when your error objective is achieved, if you meet your error threshold, or you run out of the number of iterations, right? But if you have, mistakenly encoded your training labels to a range, to a value that can simply not be achieved by your squashing function, then you are facing you are creating a poorly trained model that doesn't have to be poorly trained. So the point I'm trying to make is that remain cognizant about your squashing function, the output layer, and accordingly encode your training labels accordingly, right? Because your training process will never converge. You will stop training because of expiration of number of iterations, not because of error threshold, which is what we all hope for. Nowadays, with the advent of big data and all that, you have these new functions and the output layer called these ReLU, rectified linear units, right? So they obviously do not offer or suffer from such restrictions, right? But then that's a different ballgame, right? But the problem with ReLU is that for anything which is negative, it only outputs a 0. So in case you're using ReLU in your final output layer, then remember, you should not be standardizing your data. You should only normalize your data. If that is the case, then your data must not be standardized. You should avoid standardizing the data, but rather than you should rely on normalizing the data. Because with standardization, the data spread shifts from -1 to +1, right? Which is how you get a 0 mean. Right? So anyway, these are things that I wanted to highlight. I hope you guys will remain cognizant about when you're looking and setting up your data. Right? The next, we are almost at the end. I know I'm almost running out of time, but what if we have insufficient data? I'm so sorry I'm running out of time, but no, I'm not running out of time. I have half an hour. Okay, yes. So what if we have insufficient data, right? There are many reasons why we might have insufficient data, right? Predominantly, because you're working on a very novel problem, a problem that has not been explored by many people in the past, right? This is very, very common with in the bioinformatics domain, right, or medical domain. And if you have insufficient data, right, what do you do? What can you do? So one thing is you could cheat a little bit. You could cheat. I mean, cheating is always fun if it is done for the right cause, right? You could inject synthetic data between real data points. Now, what is the synthetic data? Synthetic data is what we, you have two real data points, and you interpolate using, linear interpolation or some nonlinear interpolation, and you generate sample points and corresponding label points between these sample points, these real sample points. You could perform interpolation between two successive points, or three continuous points using nonlinear interpolation and so on and so forth, right? And inject synthetic data. Now, my advice, my word of caution is whenever you inject synthetic data is to flag them, because it is almost certain, it is more likely that these synthetic data points may not correspond to a real output of the physical process that you're trying to model, right? They are good from a learning point of view, because this is, again, we are talking about the numbers over here, but they may not necessarily represent a viable real output of the physical process. But from a learning point of view, it is a good technique. It is to increase your data volume, to aid the notion of learning. Right? So you could perform some data interpolation. Right? What are some now? I had mentioned noise, right? So we talk about noise, right? So noise is typically multimodal and usually non-deterministic, right? Sometimes you get quasi-deterministic noise, like, for example, if you have a steady state hum in your acoustic signal that you're capturing, right? If you're capturing, let's say, acoustic signal, a sweet signal, right, and you get some acoustic hum from a power line interference, that is a quasi-deterministic sound that, if you're sitting in Asia, it is probably 50 hertz. If you're studying in Northern America or Australia, it is 60 hertz, right? So you can filter that out, right? But noise is usually non-deterministic and multimodal, right? So how do you denoise your data, right? Before I mention denoising, let me just mention one singular latent benefit of noise. If you add noise to your samples, or if you allow noise to remain in your samples, two things will happen. Dr. Preeti, do you have a question? Preeti ji, you have a question? You've raised your hand. Okay. So if there's not a lot of noise, if the noise is not too large, right? I forget, there's a test that you can perform, particularly with temporal data, is that you can test if the data is too noisy or not by looking at the number of turning points, right? I forget the name of that test. It's slipping my mind right now, but I'm sure you guys must have seen, like, if you have time series data, you can test if the data is too noisy or not, right? And it says that if the number of inflection points is greater than, I think, two-thirds of n minus 2 or n minus 3, something like that. It slips my mind right now. It's called the number of turn points, right? So it's basically saying that if your data is very noisy, it'll be very spiky. That means there'll be too many spikes along in your data, right? So, or your data series. But the only singular advantage of leaving noise as is, if it is not too high and not too much, is it allows your model to become robust. Training with noise, sufficiently not significant noise, but something less than significant noise. Training with noise allows your model to become more robust. Because remember, It is iterative in nature. Learning is iterative in nature. You're essentially changing the learning plane. If you can visualize, let's talk about two ways. If you just talk about two features, right? So these two features control your sample space. And let's say this is where your minimize. Let's say this is where your training minimize. So as you guys might have remembered, right? So X1, X2, two features, right? So you start anywhere with your training and you travel along a certain path and you reach the global minimum. When you add noise, you essentially shift these contours slightly. Right? You shift your sample's feature space, the feature plane. So even then, and yet you're forcing the convergence to reach to the same global minimum point. Right? If you can achieve that, if your algorithm can achieve that, then what you end up with is a model that is significantly more robust than a model that has been trained with a noiseless data set. Right? So keeping noise in your data set has one and only one positive connotation. And yes, it is a big one, but it is not always possible. Not always possible. So what we do as a company, we tend to clean up our data set and then add some synthetic noise, right? You'll add some small amount of Gaussian noise, which has 5% of the amplitude of the overall samples and so on and so forth, right? But that's just flamming the ashes, right? You just fanning the ashes, right? That okay, for the sake of my mental peace, I'm doing that. But in reality, with raw data, with the amount of real world noise into the data sets, training becomes much harder. Achieving your level of accuracy and performance that you're hopeful for becomes much harder. Which means that invariably you will be forced to pre-process and denoise your samples. So how do you denoise your samples? Invariably you'll perform some kind of filtering, right? Denoising means filtering, right? If you have some DC component, you can eliminate that trivially. But if you have multimodal noise, non-deterministic noise, you need to perform some kind of filtering. The problem with filtering is that it will lower the amplitude of it'll lower the magnitude of your features, right? And if you have temporal data, it can also reduce the length of the sequence. So those are two things that you have to keep in mind. Keep in mind that the filtering can attenuate your actual data and can also lower the sequence length. And this is important when you're working with temporal data, time series data, right? So that's important. Okay. Last but not the least, how do you handle missing attributes, missing features, right? I had mentioned near the beginning of my talk that sometimes sensors fail, sometimes a particular sensor will fail, data stream is coming in, and you have realized after 2 days of capturing data that your 5% of your sensors had gone down 2 hours into the data acquisition process, and now you are done with it, right? So what happens? How do you handle that, right? So and this is not something that you can get around, right? This will happen. This is a part and parcel of nature, right? Sensors fail, sensors black out, right? You have power failures, right? You have noisy channels, right? So you have a lot of reasons why samples might get corrupted, right? Samples might be missing. So one way to account for missing features is either you reject those samples, simply reject any sample whose integrity cannot be verified. That means a sample which is not complete can be rejected. Now, you can do that if you have sufficiently large number of samples, right? But if you don't have a large number of samples, then the other way to handle that is to populate the missing samples by some derived metric from the remaining good samples, right? For example, if I have the heights of 70 students in my class out of 100, and I have the no height value for the remaining 30 students, Now, one good way is to populate the remaining 30 with their height values at the average height of the 70 samples. It's not ideal, it's far from perfect, but it is not as bad as something else. Right? So you could populate with either the mean value or the mode value, if you will, right? So what I'm saying is some derived metric. So two ways of handling missing features. You can either reject the samples or you can populate samples using some derived metric. And last but not the least, always randomize the order of the training samples before you feed it to any learning algorithm. Any. Always randomize. Now, the good thing is for us nowadays in this day and age is that every known machine learning algorithm will do that for you on its own. It assumes that it will need to randomize the samples. But purely from a theoretical learning point of view, like from a conceptual point of view, you always randomize the order of the training samples. Right? Last but not the least, variety and redundancy. Try not to have too much of redundancy in your data. 2 to 3% redundancy, 5% redundancy is all right if your volume is large enough, right? But what is critical is you must have samples belonging to an almost equal number of samples belonging to every class that you want to tackle in your machine learning problem. If you're doing a classification problem, if you are doing an identification problem, right? And you're trying to figure out how many classes there are, or which class a particular sample belongs to, then during the training phase, make sure that your training data set contains an approximately same number of samples for every possible class that your test data will feature or will arise from. Right? So more or less an equal number, but variety is much more important. Right? The remaining 3 points are pretty much self-explanatory. That when you're splitting if you have a static data set and you want to split it between training and testing, always a good idea to allocate the majority for training and the remaining for testing and validation. Traditionally, people nowadays use 70-30 or 75-25 ratio between training and testing. And the one good thing that you must, or one key thing that you should always keep in mind is that your training and testing databases, right? Training and testing samples must be disjoint. There should not be any overlap. So you should always test on samples that have not been seen by your learning machine. When I say not been seen, I'm not saying from a label point of view. I'm talking from a feature space point of view. So, no overlap between testing and training data sets. Some last points. I am almost out of time because I believe I'm supposed to give about 10 minutes for Q&A. Data is obviously not the end of the story. If your model is not performing to your satisfaction, don't panic, don't lose hope, don't give up. Step back, reassess. Why? Remember, machine learning is mostly heuristic. Right? There are no hard and fast rules. Right? I'll give you an example. Right? With ANNs, they say that if there are too many weights, like for example, if you have too many weights in the network, right, with respect to the available data, a good rule of thumb is that the total number of is what you call as the n by 10 rule, right? So it says that the total number of weights in the network, in your artificial neural network, should not be more than 1/10 the total number of samples or training samples. It's a good rule of thumb. It's in fact even mentioned in a book, right? A very standard machine learning text. But I have never found it derived or proven anywhere. Right? So, and the reason why do they say that is because this rule has been found through experimental testing to provide the most optimal compromise between performance, network architecture, and the volume of data available. Right? Performance of the model and the data volume. So if your ANN is not giving you sufficient performance, step back, reassess. Maybe I can reduce my hidden layer architecture. Maybe I can reduce the number of hidden layers, right? And so on and so forth. Maybe I can modulate my nonlinearity sitting on the hidden layer. And that kind of stuff. Maybe I need to maybe I have not scaled my input feature space. Right? Maybe I can use a different kind of learning machine. Maybe I don't need to use ANN. Maybe I can go back to, if I'm doing a binary classification, I could get away by using support vector machines, right? That kind of stuff. So, my point is that just reassess, right? Because learning algorithms, learning AI, ML, this is something that you get better with the more you do it. The more you do it, right? The more number of applications you work on, the better off and the more insightful you'll become. Right? Anyway, guys, that's all from me. Any questions?